Hi, welcome to AP Physics C Unit 4. This is topic 4.1. And so in this video, we're just going to really discuss what linear momentum is. So just a little bit of a heads up on the test, whenever they say momentum by itself, they're talking about linear momentum. They're not talking about angular momentum, which ends up being in Unit 6. If they're going to talk specifically about angular momentum, they will say angular momentum in the question. So anytime you see the word by itself, momentum, we're just talking about linear momentum. So linear momentum is going to be defined by the equation P is equal to mv. So something to note that it is a vector. Another difference between physics 1 and physics C is that here in physics C, you may run into two-dimensional collisions later. So you may have to break up that velocity vector into components, okay, by using sine and cosine. So like if you're looking for P sub x, it'd be mv cosine theta. If you're looking for P sub y, it'd be mv sine theta. Again, the cosine and sine go based on the angle that you know. And again, in physics, we like to use the horizontal angle and not necessarily the vertical angle. Okay. So again, we just mentioned this, how momentum is a vector quantity and it's going to point in the same direction as velocity. Another way to define momentum, and this is something, when we define it in an algebra-based course like Physics 1, we call it inertia in motion. So as a mass begins to move, and now it starts to pick up its momentum. And so momentum, it's going to be used to analyze collisions and explosions. So here are the definitions of the two. So collision, it's a model of interaction where the forces involved in the system, or between the involved objects in the system, are much larger than the net external force exerted on those during the interaction. And explosion is a model of an interaction in which forces internal to the system move objects within that system apart. So two common questions, right? Two cars collide. There's a collision, and then you could have an explosion like a cannon being fired, okay? And this is the reason why cannons now have wheels, or in modern cannons, that's why the barrel recoils, okay? Because of this fact that there is an interaction going on, right? The forces inside are going to push the cannon and then the cannon or the projectile in opposite directions. So let's look at an example problem. And the example problem is more conceptual based. It's something that shows up in a multiple choice question every once in a while. So we're gonna do two derivations, right? So we're gonna derive an expression for the kinetic energy in terms of momentum. So we're gonna have K in terms of P, and then we're gonna derive an expression for momentum in terms of K. So here then we'll have P in terms of K. So if we take, So if we take the two equations, P equals mv and K equals 1/2 mv squared, okay, we need to solve, and note that they both have v in it, and that's going to be our defining factor, right? So in the part A, I'm going to take the momentum equation and solve it for v. And then I'm going to take this and plug it in for v squared. So I have let me start with K equals, right? So K equals 1/2 mv squared. I'm going to plug in P over M. So I have 1/2 P over M squared. And I forgot the M from the kinetic energy equation. And so we have 1/2 M P squared over M squared. All right. And then what happens? One of the M's in the denominator cancels the M up top. And so we just simplify. So kinetic energy in terms of momentum is going to be P squared over 2M. Okay, now let's go to the other side where we're going to derive an expression for momentum in terms of kinetic energy. So again, we start with our two basic equations, but this time we're going to solve the kinetic energy equation for V. So V is going to be the square root of 2K over M. And then I'm going to substitute that into the momentum equation. And so you would have P equals mv. So P equals m times the square root of 2k over m. Now you can leave it as that, or let me make my m a little bit nicer. Or we can take this m in the bottom and bring it out as m squared, right? Actually, no, we can't do that. Sorry. All right. But actually, what we can do is take this. Oh, I didn't mean to erase it. So I have m times, so I can take this and bring it in as m squared, right? And then I can do some simplifying. So we do the square root of 2m squared over k. Okay, and why can we do that? Because if I pull out that m squared, right, the square root of m squared is just m, right? And so I can take that, one of those m's cancels the m on the bottom, and you end up with the square root of 2m times k. So there is momentum in terms of kinetic energy. Okay, so in the next video, let me just double check my notes here. I think we're going to, topic 4.2 is going to focus on impulse and momentum. Okay, so we're going to, so the topic is called change in momentum and impulse.